one, we're still not there. Well, I added one additional reference. So I'm going to begin with answering a question that came up last time, and that was, how does the London equation, you remember this equation that gave you J in terms of the vector potential, mean you have superconductivity? In other words, zero resistance, right? And so that's what we're going to talk about once. Switching this backwards and forwards take 2 minutes. This comes on. Okay, good. So these were the references I had last time, but after we talked at lunch, Henri reminded me that if you want to see a little discussion of superconductivity from an experimentalist perspective, you should read his book. And so I've added it here, chapter 18 of Henri Allour's book, Introduction to the Physics of Electrons and Solids. Very nice introduction. If you have any questions about it, or if you'd like to get a free copy, just talk to Henri, okay? Okay? So last time, here's the question that came up last time. How does London's equation imply superconductivity? Okay? So I thought it'd be a good place to step off at the end, right? And you may remember last time that we had this expression here, right? So let's look at what conductivity is implied by this expression, okay? And the way we're going to do that is that we're going to first, we wrote it as J equals minus NE squared over M. We're going to write it as a function of frequency under the assumption that at low frequencies, this quantity here doesn't change, so it's frequency independent, okay? So just remember now that E is equal to minus dA by dt, right? Which means that if you Fourier transform that, d by dt is minus I omega. So E of omega is equal to I omega A of omega. So we can just replace A of omega by E divided by I omega, okay? And so when we do that, that gives us the conductivity as a function of frequency. And look, the conductivity has this very weird form, okay? And this 1 over I omega, remember, 1, the Fourier transform of a delta function is 1. The Fourier transform of the integral of a delta function, which is a Heaviside function, is 1 over I omega. So this just says that if you put on a pulse of electric field, which would mean that you have a frequency independent E, okay, then the current switches on after that and remains fixed. That's what it tells you, okay? But we can look at the frequency dependence of this thing, and it's customary to look at the retarded conductivity, which is omega plus I delta. And so that adds a little bit of delta into this expression. And this begins to look a little bit like what you're familiar with from Drude conductivity. Let's expand this out as a real and imaginary part, okay? And the way we do that is that we write it as 1 over omega plus I delta. And then we remember that 1 over x plus I delta can be expanded into the principal part, 1 over x, minus I pi times a delta function. So if we now write this out, it takes this form where we can read off the real and the imaginary part of the conductivity. And notice that almost all of the conductivity is reactive. It goes like 1 over omega, okay? And that's a sign of a superconductor. But in addition, there is this little delta function here, okay? It's not a little delta function. It contains a huge amount of weight in it, weight pi, okay? And if we plot that thing, then that's what the conductivity looks like of a superconductor. It has a finite frequency part and a bit that you can't really measure except by measuring the penetration depth. In fact, the weight of this, NE squared over M, apart from a mu naught, is 1 over the penetration depth. So if you know the penetration depth, you know how much weight is here, okay? But this quantity here is also omega plasma squared, apart from an epsilon naught, okay? And in fact, what's really happened here, let's compare with Drude theory. Drude theory gives you this, okay? The Drude theory also, if you make it, put it into the frequency domain, you replace the 1 over tau inverse by tau inverse minus I omega. Okay? And so this has a Lorentzian real part and a omega times the Lorentzian imaginary part. So let's look at what that looks like, the real part of that, and superimpose it there. Okay? And so what you can see here is that the Drude peak, which is this thing here, has collapsed into the delta function at the origin. The Drude peak has area pi times ne squared over m. And all of that weight has gone into this peak here. Since Henri's in the audience, he says theorists always do this. They show you the theory, and then they show you a piece of data that fits the theory perfectly. Actually, almost no data on superconductors fits this theory perfectly. Okay, this is just an idealization. Just to quickly show you some data, okay? Here is niobium, okay? You can measure the optical conductivity either by doing transmission through a thin film or from reflectivity. And here is the Drude behavior of niobium in its normal state. I guess at 9 Kelvin, its TC is 8.3 Kelvin. And as you cool it down, you see the transfer of spectral weight actually into a delta function, which you can't even see. But you can see here sigma 2 and this 1 over I omega component developing as it goes superconducting. And here is the penetration depth squared as a function of temperature. Okay? This is lambda 1 over lambda squared as a function of temperature. And this part does fit a BCS theory, which we still haven't talked about yet. Let's compare that with a Cuprate superconductor. Okay, this is a Cuprate superconductor. This is an underdoped, and this is, I think this is a slightly underdoped. This is a seriously underdoped system. Okay, and what you see here at optimal doping is that a gap is carved out of the. Well, first of all, in the normal state, this is the Drude peak. This is the Drude peak of the strange metal. And as it goes superconducting, you can see the weight descending into the delta function peak, which you can't see here, of course. One of the interesting things about the underdoped is that this trough in the conductivity is actually developing before it goes superconducting, as if locally it's developed some kind of superconducting features. Right, so that's the answer to the question that was posed, and I'm going to come up with a second answer to how a superconductor is superconducting in a few minutes, one that links to topology. Did you have a question, students? There's a student there. Andre, what was your question? Yes. The sum rule works for any. The F-sum rule Andre asks about is the area under the optical conductivity is a fixed number. That area tells you the instantaneous response to a pulse of electric field. So that area up to constants is basically the Ne squared over m that we saw last time. And it's the same for all conductors, or insulators, all everything. Okay? Does that answer your question? More or less. I'm not going to go and do I thought about it, but I'm not going to digress into the optical sum rule. Okay? Okay, good. So now it's time to flip this thing up. Where's the button? This one? There we go. And we just pull the plug, and we just turn on the lights. Become a star. Okay, thank you. All right, so les II. Okay. Oui, mais il faut éteindre. So today we're going to talk about. Good. Okay. Today I'm going to talk about Ginsburg-Landau theory. And we're going to do this by steps, okay? You may remember that in the London equation, which we're going to write down, there was, I can't go in there. Okay, so there's this mysterious psi, which London thought of as a kind of macroscopic wave function. So we're going to digress, and we're going to talk a little bit about what that means, okay? And so, in short, our modern understanding of a macroscopic wave function is as a condensate. Okay? In the context of BCS pairing, the boson that condenses is a pair of electrons. In the context of a neutral superfluid, such as helium-4, made a bosonic superfluid, that condensate is a condensate of bosons. Okay? And so the primary field that condenses is a boson. It could be a composite boson, or it could be a boson in its own right. Okay? And so who here knows what a field operator is, a creation operator? Okay, almost everyone. That's good. Okay? So a field operator, this guy here, when I dagger it, creates a boson. This destroys a boson at that very site. Okay? And the order parameter of a superfluid or a superconductor, where this would destroy a pair of electrons, is just the expectation value of that field. Okay? And this has an amplitude, which is, we call it the superfluid density, can depend on x. Okay? And it has a phase, which can also depend on x. Okay? And now let's stop there. Okay? Because when we learn quantum mechanics, we're taught that, first of all, the phase of a wave function is not an observable quantity. In fact, the wave function is not an observable quantity. It measures probabilities of finding a particle at a given place. So writing down this formula seems to go against everything we were taught in one-particle quantum mechanics. Okay? Seems to go against the Bohr interpretation of quantum mechanics itself. So how can we do this? What does that mean? Okay? And that's going to be part of our discussion today. Another point that we're going to be discussing, of course, psi squared. Normally, that means the probability of finding a particle at a given point, but in a condensate, it measures the density of the condensate. Okay? And in a neutral superfluid, well, when we bend the phase, we give a particle a velocity, and we're going to identify the superfluid velocity with h bar over m times the gradient of the phase. And when it becomes superconducting, this will involve E star, which is going to be 2e, times A, to make it fully gauge invariant, okay? Right, so, but if E star is equal to 0, then we have a neutral superfluid, okay? So, let's make a further digression on this, okay? Let's try and connect this up with one-particle quantum mechanics. And so my digression is going to go here, because I need space, okay? So remember one-particle physics and classical physics, one-particle physics, which is already amazing in quantum mechanics. When we learn classical mechanics, we learn about phase space. Phase space, x, or q, and p, and the particle just sits at one point in phase space, and Hamiltonian dynamics moves it around in phase space, okay? But when we think about quantum mechanics, we learn that particles are waves, and that if you want to do this stuff, you need to think about a wave packet. And that wave packet has some uncertainty in position, okay? And it also has an uncertainty in momentum, and it lives in some region of phase space here. This is delta p, and this is delta x. And of course, these two things cannot be measured with arbitrary precision. Delta p, delta x is greater than of order h bar or h bar over 2. And as operators, x and p do not commute. Okay? And one more thing about this. Let's look at a harmonic oscillator. Here's my harmonic oscillator potential. Okay. When I put a particle into its ground state, this is V of x, and this is x, okay? It undergoes zero-point motion, and so the ground state wave function is something that looks like that, okay? And in operator language, we call that thing the ground state, okay? Right? Put it over here, okay? But we can make wave packets on this by a very simple device. One of the things we learn in one-particle physics is it's very useful in a harmonic oscillator to combine x and p into a complex operator, which is of course, the elementary annihilation operator, and I'm going to put it like this. Write it like that, okay? And so now supposing we want to give a particle a given position at position x naught and position p naught, okay? If we want to boost this, what do? Well, we combine x naught and p naught into one number, call it z, write that as x naught plus I p naught. Again, I'm going to normalize it like this, okay? And then, to create that state, what we do, which is located at z, all we do is we act on this vacuum state with something called a coherent state operator. It looks like this, okay? This is the story about harmonic oscillators you're probably never told, okay? But this operation here, when you multiply this out, shifts this guy from sitting here, okay, and sends it out to there. Okay? Right? And in fact, this is a wave packet when you work it through. Okay? And this is a wave packet. It's a coherent state. It's a wave packet in momentum space, in phase space. Now you learn that blackboards are smaller than a piece of paper, because I wanted to do the second half down below, but of course I can't. And now I've got a dilemma, because I either erase that or I go left, so I'm going to go left. Okay? Right? So in many body physics, we have a very similar situation. In many body physics, we don't live in phase space of p and x, but we live in a Fock space. Okay? And one of the remarkable things about this little operator, psi of x here, is that this is the operator that takes you on your journey around Fock space. And of course, Schrödinger introduced the many-body Schrödinger equation, which we use still very much so in many-body physics, in chemistry. But one of the more beautiful ways to describe many-body physics is to use field operators. And these things take you from a state with n particles to a state with n minus 1 or n plus 1 particles. Okay? They're very weird things. Okay? So let's now talk. Well, I suppose I'm just going to just start here, and we'll digress. So in many body physics, we use a Fock space, okay? And psi of x, this field operator, destroys a particle. At x, okay? And whereas this guy here has the canonical algebra B with B dagger equals 1, okay? This guy here has a very similar algebra if it's a boson, psi of x with psi of y, dagger equals delta of x minus y, and this would be in d dimensions. Okay? So what does it mean to give this thing an expectation value. Okay? Well, this state here, by the way, I didn't actually mention it, has the property that when I act B on the state Z, I get back Z on that state. So this coherent state is actually an eigenstate of the destruction operator. Okay? And is everyone okay with that? Do we need to prove it? Okay, well, we can prove it. It's yet another digression. I think I'm not going to do it here. Okay, if you don't know it, too late. Okay, but the way you can prove it is you can expand this guy. We'll look at that in a second. You can expand this guy as a power series in Z here. Okay, and you can use the fact that B with B dagger equal to 1. You can then use the fact that B with B dagger to the n equals n B dagger to the n minus 1. And you can act on this state and show that this is true. Okay? Right. We can form a similar coherent state with bosons here. And the way we do it is that we create a boson which creates, I'm going to do this in 3 dimensions, which creates particles with weight psi of x. This is a number, this is an operator. I apologize for the ambiguity, but the hat breaks the ambiguity. Okay, that means an operator. And I'm going to divide this by the number of particles in the superfluid.
I'm sorry, is this number psi the same as the number psi you have in the program?
Yes, it is. It is. Sometimes when you do math, you have an ambiguity of notation, and so I'm just warning you about the ambiguity of notation here. This guy here is exactly this guy here. And we're now going to create the state in which this is true. Okay? And it'll be no surprise to you that that state is, too many psi's here, is just a coherent state. I'm going to write it like this, where we choose Z equal to the square root of ns e to the I square root of ns. This is a true statement. Okay? What this does is it creates a particle all over space with amplitude psi. Okay? And this state here is rather interesting. We can, of course, expand it like the other guys. It contains the vacuum, and then it contains the term linear in B dagger on the vacuum, and then we can keep going up, and the general term is Z to the n, B dagger to the n, over 0, and we write it like this. We split the n factorial up like that, because this state here is an n-particle state, properly normalized, and so this is actually the summation over Z to the n times an n-particle state. So this is a coherent state, and it has the remarkable property that psi, the operator, acting on this state, is actually equal to psi, the number, acting on that state. I'm not going to prove that, but the way you do that is really quite straightforward. The steps are, you take this is B dagger here, sorry. You take the commutator of psi, the operator, with B dagger, psi, the operator, with B dagger, pulls out this thing here and gives you a 1 over the square root of ns times psi of x. Okay. This commutator, okay, this is the commutation relation. If you now apply that to this expansion here, you can easily prove this. And so this is the state in which this guy, this field operator, is condensed to have an expectation value psi. Okay? And when I write, there are a few things that we have to work out here that are a little bit more complicated. It turns out that the overlap of psi with itself is e to the z bar z. And z in this case, well, actually, it's e to the z bar z over ns when you work it out, I guess. And when you work that out, it's properly normalized, so this is actually equal to 1. Okay? And so when you calculate expectation value of psi of x in this state, you sure enough get ns e to the I phi. Yes.
Are you really saying that e to the 1 is equal to 1?
No, I'm not. I'm just getting confused. I'm going to just erase this for the moment, okay? And I'm just going to normalize it because I've forgotten my normalization. Yes, good. Good question. Okay, so we really can form a state in which this is true, and in these states, there is an uncertainty relation, of course. And just like in one-particle physics, the momentum operator translates position. Well, in many-body physics, the particle operator translates phase. Okay? What I can do in this is I can write this out as square root of ns x e to the I phi of x. Okay? And now look at what happens if I act with this state. Let me just use the shorthand psi and call that phi, just looking at the phases. If I take the state phi and I act on it with e to the I alpha n, where n is the total particle operator, then acting this on the state phi actually translates phi by an amount alpha. And the way you can see this is that you can see that every time I commute this operator, e to the I alpha n, with psi of x, I can write that as psi dagger of x, e to the I alpha, e to the I alpha n. Has that property. And so when I pull this all the way through this exponentiation of operators, I just pick up e to the I alpha for every boson I pass, okay? And because every boson I pass has an e to the I phi with it, it just translates phi of x into phi of x plus alpha. And so what this means is that the number operator is rather similar to, remember that e to the minus I alpha p acting on a state x gives me the state x plus alpha. Okay. And so phase and number operator bear the same relationship as momentum and position. Okay? In fact, you can actually see that the number operator can be written as the differential with respect to phase, just like the momentum operator can be written as minus d by dx up to an h bar. And what this means is that there is, in fact, a uncertainty between phase and particle number, okay, which is I. Now, what that means is that if we look at one of these coherent states, they have to satisfy this behavior here, right? Supposing I want a uncertainty, so this means that delta phi, delta n is greater than of order 1, okay? So for one particle where delta n, if you make delta n equal to 0, equal to 1, sorry, if you make delta n equal to 0, delta phi becomes infinite, okay? But supposing you want to make delta phi, make delta n equal to 10 to the 11. Okay? Supposing you do that. Now, you might think that's ridiculous. That's such a large uncertainty. But delta n, when n is equal to 10 to the 23, this means that delta n over n is actually 10 to the minus 12. That's good enough precision for anyone in the Newtonian world. That is Newtonian precision. And what this means is that delta phi can now be of order 10 to the minus 11. That also is Newtonian precision. And so when you form a coherent state, which you really can do, okay, a state with an imprecise number of particles, you're basically forming a wave packet in Fock space. It's a wave packet where the location, instead of phase space, x and y, what you now have is the real part, psi 1, and the imaginary part of the field operator, and you're sitting out here at angle phi, and you've got this little wave packet here, delta psi 1, delta psi 2. Well, I don't want to write it. So delta phi, delta n, is greater than of order. This length here is the square root of the number of particles, well, I don't know what I'm doing here. This is basically the number of particles, okay, and this is phi here. Okay, and so we can have such a state. It has an uncertainty in density of 10 to the minus 12. It has an uncertainty in phase, which is 10 to the minus 11. And so on this picture here, the uncertainty is such that it's just a dot you can't even resolve. It's a perfect point, okay? And so this is what I mean by a condensate which has a well-defined phase and a well-defined well-defined phase and a well-defined field operator. It's basically classical physics. It's the classical limit of a coherent quantum state, many-body state, okay? Now, with that digression, let's come back to these equations, okay? And let us move on and talk about Ginsburg-Landau theory. Questions? Okay, good. Okay, digression over, half an hour has been absorbed, but that's fine. Okay, so the coherent state, by the way, was developed in both particle physics and in optics. It's the way you describe a laser beam. And they're often called Glauber states. And Roy Glauber received the Nobel Prize for his contributions in developing these ideas of coherent states. After all, a laser is nothing more than a photon condensate. And when you deal with classical fields, when you set up a capacitor or you set up a low-frequency electromagnetic wave moving across, what you've set up is a photon condensate. And when you describe electromagnetism classically, you're basically describing the center of mass motion of these packets of photons, okay? All right, good. So, okay, so when we set off last time, we had this length scale. I'm coming back to that now. Here it is x, okay? And there's some length scale which we call the coherence length we're going to come back to. And we're going to see that when we are dealing with length scales longer than the coherence length, amplitude fluctuations of this condensate can be ignored. So what are we going to be doing? We're going to be starting out with a free energy for this order parameter, and we're initially going to think about neutral superfluids. Just a 5-minute discussion of neutral superfluids, then we turn on their charge. Okay? So a neutral superfluid, according to Ginsburg-Landau theory, has a free energy density. And we're going to model it using the Ginsburg-Landau functional, which is a functional of psi and the gradient of psi. Okay? And that Landau-Ginsburg functional, well, let's write it down. First of all, it contains the part that Landau invented. Okay? It's just a polynomial expansion, and this term here is A, T is the mass of the field. It's the term which changes sign at the phase transition. Okay? This is the interaction. And this field here is complex. So psi is psi1 plus I psi2. Okay? And so this little picture here we'll come back to, but before we go on, let's now add in the gradient term, S grad psi squared. Okay? And that's it. All done. Excepting if this is the energy density of this field, then this is basically the expectation value of the Hamiltonian. Okay? And so this is really a condensate of bosons, okay, which this term here comes from their static energy, their chemical potential, if you like. This term here is their interaction. And what is this term here? Well, this term here is nothing more, S grad psi squared, is nothing more than the kinetic energy density, which is h bar squared over 2m grad psi dagger grad psi. And so we can identify this term here as h bar squared over twice the mass of the boson. Okay? And this is nothing more than the expectation value of the Hamiltonian in this coherent state. Okay? Now, that's what it is. And we can do a lot of things with this. Let's just look at it very gradually, right? Let's first look at it without the gradient terms. Without the gradient terms, f is just r psi squared plus u over 2 psi to the fourth, okay? And this quantity here is a phenomenological quantity which changes sign at Tc, and so this free energy functional just looks like this. It looks like a parabola with a little bit steeper at the higher. This is now psi, and this is f of psi. And this is what it looks like, provided T is greater than Tc. But if we go below Tc, it has a negative curvature here, and so the ground state shifts from here to there. Okay? And you can work out that psi is equal to A Tc minus T divided by U at this minimum here. The way you do that, you just do df by d psi squared equals 0. That gives you r plus u psi squared. And therefore, psi squared equals minus r over u equals a Tc minus T over u. Okay? But there's a phase there. We mustn't forget that. This is T less than Tc. So that phase being there means that we have to realize this is not an Ising variable. It's actually a variable with a phase, and now we get to test our drawing skills. So let's try and draw this picture with a phase. We draw a little bowl like this, and we draw this coming down and going up like that, okay? And now we draw the fact this is round, and that there is now a bottom to this here. And so now our state is sitting here, and there's an angle phi here, okay? And this is the magnitude here of mod psi. And so this phase is the phase we were talking about earlier, okay? And moreover, we can extract this superfluid velocity very, very easily. Let's go and look at that we can do it in various different ways. We can remember that the current density is our minus I h bar over m psi star grad psi minus psi grad psi star. That's true for one particle, it's true for many particles in a single condensate, and if we now expand this out, we find that this is equal to mod psi squared h bar over m gradient of the phase. Because gradient of psi, if you work that out, contains two terms. It contains the gradient of the modulus of psi plus I times psi times the gradient of the phase. I guess I have to put e to the I phi in front of that. So if you take this gradient here and plug it into there, the terms with the gradient of psi are the real part of it, but this extracts the imaginary part of this quantity, and so it just picks this term up here. And using our interpretation that this is the density of the superfluid, we can see that this is equal to ns, and this term here we then interpret as Vs. It's the superfluid velocity. Okay? So I've now explained to you this part of the story. Okay? Right. We can do one more thing with this. We can extract the coherence length. And the way we do that is that we rewrite this. Let's rewrite this Landau-Ginsburg expression as, well, we rewrite it as f psi, and let's pull out the h bar squared over 2m from the Gaussian terms and write it as grad psi squared plus 1 over some length scale psi squared. And all I've done here is I've rewritten h bar squared over psi squared equal to r. So r equals h bar squared over 2m psi squared. Have I really done that? Sorry. That's right. And by the way, this is also equal to s over psi squared. And therefore you can see that psi is equal to s, I'm going to write it like that, over the modulus of r, which is h bar squared over 2m modulus of r. Okay? And in fact, this is also, r is at minus t naught, so I'm going to write it tc minus t. Okay? And good. And we can also write that as, in the following form, as psi naught times 1 minus t over tc to the minus a half. Okay? And this quantity psi naught is the zero temperature coherence length. It's psi at t equals 0, which is h bar squared over 2m a tc. Okay, that is the coherence length. Let's stop for a second. So we're done, for the moment, with superfluids. Excepting, let us ponder for a moment at this expression here for a superfluid. Because it answers something very, very important we're going to come back to about superflow. It's an incredible equation. It tells you that when you twist the phase, you get a current. Okay? This term here tells you, from the point of view of an elasticity picture, that a superfluid has developed a phase rigidity. Okay? And when you twist the phase, you develop a current. When you twist the phase, you're changing the ground state. You're not really exciting particles above that ground state, you're just deforming the ground state. And so this current is really a property of the ground state that's been deformed. So now, if you get a bucket of helium-4 and you send it round a tokamak, a donut, and you cool the tokamak down, cool it down, it goes through the superfluid transition, viscosity disappears. You've now set up a state with a uniform phase gradient. If you now integrate that phase gradient around the loop, the integral of the phase gradient around the loop is the total change in phase as you go around the loop. But that's 2 pi times n. That is the integer invariant of this topological state, because you've developed a state which has got a winding number of the order parameter. And we discovered yesterday that when you have a winding number of the order parameter, that's described by homotopy theory. Let's draw a little picture before we leave our superfluid and go to a superconductor of that donut with the supercurrent running around it. When I first arrived at Rutgers, they used to do these experiments. They had a rotating cryostat that you could actually set up. Anyway, so here is the donut. Okay, here is the superfluid velocity, and if we calculate the rotation of this, which is v dot dx around this loop, if I integrate this around the loop, then this rotation is h bar over m times the gradient of the phase around the loop. But this is nothing more than h bar over m times 2 pi n. So the circulation is quantized in units of n. And it's a topological invariant, which means it will stay there unless you mess with it in a serious way. The only way to stop this from rotating at that level is to send a vortex through from one side to the other. But that costs a lot of energy. It can happen spontaneously in the ground state, but when that happens, it's a 0-point fluctuation, and the amplitude for the thing to occur is e to the power of the action. But the action is large. It's classical. And so when you divide it by h bar, you get an e to a very large number, which means the time scale for this thing to occur is extremely long and very rapidly expands as exponential to the number of particles. And so the time scale becomes very rapidly the age of the universe, which is why topology sustains a superflow in a superfluid. And it's the same principle that sustains the superflow in a superconductor. And so it's the topology of the order parameter, the fact that pi 1 of this order parameter space, which is U1 or S1, is equal to Z. It's this mathematical expression that gives rise to persistent superflow and supercurrents. Superfluidity and superconductivity have a topological origin. Okay, right? If you now were to take the order parameter and make it into a vector rather than a 2D vector, but a 3D vector, you would now change this to S2. And it turns out that pi 1 of S2 is 0. And so whereas an XY magnet is actually a kind of spin superfluid, a Heisenberg magnet is as dead as a doornail. It doesn't have this topological feature to create vortices. And what that means is that were you to set up an attempted vortex in a Heisenberg magnet, it would rotate into the third direction. So now here's the thing connected with high TC. Some people believe that the order parameter acquires additional dimensions, additional components, when in the underdoped superconductor. It was the original idea of Su-Cheng Zhang of SO5, okay? Once you create an order parameter with additional dimensions, the homotopy dies and the superconductivity will disappear. And so that's one of the reasons why there's a lot of interest in the pseudogap phase as being some exotic order parameter with additional dimensions. Okay? Right? Okay. Okay. So all of those digressions, but now we have to turn the charge back on, okay? And what that means is that we need to think about gauge invariance, and we learned last time, and nothing different, that when we think about gauge invariance, we have to think about the so-called minimal coupling of the condensate, the field, to the vector potential. So now we're going to write, yes,
Before you go to the superconductor,
yes,
perhaps a little remark on the topology that you're talking
very good.
I mean, here it's not the topology really of the order graph. It's the topology of the manifold that your order graph lives on.
Absolutely. That's
Taking this totals, I mean, you're perfectly allowed
right.
to classify that.
Yes. Yeah.
Topological invariance,
Right.
but it's not that much the order parameter itself that is topological. What will become topological, and there you can use also the same type of classifications, is once you put the defects in it, which are just the
That's right. So I'm being glib here, okay? I'm using a physicist's prerogative to call it an order parameter that is topological, but you're quite right. This is not a quote-unquote modern topological superconductor, but the order parameter has topological properties because it lives in a manifold which has this non-trivial homotopy. Perhaps a better way of saying it. Thank you. Okay. Yes?
Does it describe all the supercurrents?
Yes, it does. Every single one. And that's the amazing thing, okay? We can be quite sure that this homotopy is a property of all superconductors. And so once we go beyond the coherence length, all of this physics is good. There are some little bits and pieces that I haven't talked about. For example, if you had a p-wave superconductor, the condensate also carries spin. And so you have to put that feature into the order parameter, and it's a little bit more complicated, okay? You could also imagine a condensate with two complex components. That's where we live. That is the vacuum. We live in a vacuum of a Higgs condensate. And the Higgs condensate has a coherence length somewhere around 10 to the minus 18 meters, and we don't know what lies beneath it. But we do know we live in it, and we do know that the Higgs phenomena, the Anderson-Higgs phenomena that causes magnetic fields to be expelled from a terrestrial superconductor is the same effect that causes the Z and W fields to be expelled from our universe and gives us just one leftover field, the thing you can see me with, which is the electromagnetic field, okay? And so this physics is truly universal. And the discovery of Landau and Ginsburg, and later its embellishment and deeper understanding, perhaps by Anderson, lay the groundwork for the electroweak theory, okay? And as another digression, it's quite probable that the work we are doing in our field today to understand other unsolved problems, such as strange metals, will lay the groundwork for the next generation of discoveries in particle physics, okay? That was recorded. Good. Okay. So here we have two parts now. We have the electromagnetic and we have the Ginsburg-Landau part. Okay? Let's write this out in its full glory. It is, we'll keep it ddx, and now here we go. We have this stiffness, h squared over 2m. Okay? And now we must introduce the minimal coupling that's necessary to maintain gauge invariance. Okay? This is the minimal coupling. Sorry. Okay. And this term has the property that when I take psi to e to the I alpha psi, and a to a plus h bar over e star grad alpha, that it's invariant up to a minus sign, which I might have forgotten. Okay? Right. And then going on along here, we have our next terms, our r psi squared and our u psi to the fourth. Okay? And then this part here is our Landau-Ginsburg part. And now this part here, well, we're really only interested in magnetic fields, and so we're just going to write the magnetic field term in. This is F electromagnetic. This is just B squared over 2m, 2 mu naught. Okay? And in fact, if we take the, it couldn't be anything else. Once London wrote down his expression, it inevitably led to this. And it's apparently true that Ginsburg, during the war years, when he was mainly working on other activities, as a hobby, he was fascinated by London's ideas and how he might convert the psi of London's theory into the order parameter of Landau's theory. And so after the war, 1949, they got together and they wrote down this action here. They had tremendous arguments. The published paper had E star equal to E because Landau boldly asserted that he had a gauge invariant proof that it had to be E. Okay? Ginsburg was much more hesitant, as he told the world in later years when he often gave talks. He wished he could have persuaded Landau to have put the star there. Okay? We, of course, know that in BCS theory, because you need to condense an even number of fermions to make a boson, this must be an even number times E. And in fact, in all known superconductors, E star is equal to 2E. Okay? We have 30 minutes left to do all of Ginsburg-Landau theory. Of course, we're not going to achieve that, and we may well end up having to do a little bit more in the next lecture. The prospect of me showing you my solution of high TC becomes ever and ever dimmer, but nevertheless, I can tell you things that are true. So let's look at this beautiful theory. It's really two intertwined long wavelength actions. This, of course, is the action that Maxwell gave us. Okay? But if you turn everything else off, you can see that there's an a squared term here. And so it's really Maxwell's action plus a squared. Since this is 1 over length squared, this term here must be psi divided by length squared. That length squared is the penetration depth. Okay? So we can immediately see, if we now turn off everything, except if we make psi constant, and we throw this term away, that this thing can be written as if we make psi equal to a constant, then the electromagnetic part of this thing is 1 over 2 mu naught times curl of a squared plus 1 over lambda L squared, a squared. Okay? If I make psi constant, then you can immediately read off that 1 over lambda squared is the coefficients here is equal to mu naught times ns e squared e star squared over m. Okay? Where ns here, oh, that's right. Okay? So that's the first point. So it has the penetration depth into it. Okay? But it also has the coherence length. So we have our penetration depth, lambda L, which I'm going to rewrite as m over mu naught E star squared ns, okay, which I can also write if I use the fact that psi equals whatever it was, psi equals the square root of r over u, which is a tc minus t over u. I can write this in that longhand way as u times m over mu naught E star squared a tc minus t. Okay. But there's also the coherence length, xi, that we saw before, which is equal to R over h bar squared times 2m. Sorry, R over h bar, sorry, R over S, which is 2mr over h bar squared. This is, sorry, making a mess of this. 1 over psi squared is R over S equals 2m R over h bar squared. We can write that out, and that gives us psi h bar squared over 2ma tc minus t. And this is the coherence length. Okay. And last but not least, we can see that lambda L, and we can set t equal to 0 in some loose way to get lambda L 0 and psi 0. So here is psi of t, and as we cool down, it gets shorter and shorter and eventually stops at psi 0. Psi 0 is the thing we normally quote, and this is, of course, only an approximate theory which you should use just as a kind of cartoon of the physics. That is the t equals 0 coherence length. Okay. So there's a huge amount of physics encoded in this beautiful theory. And it's a very nice example of emergence at all levels. Because on the one level, this is already an emergent theory. Psi here comes from microscopic physics that we haven't really talked about. Okay? But on another level, encoded in this is the physics of that levitating train, of flux lattices, of flux quantization, of the Josephson effect. All of this is in this one equation here, okay? And so even if you have a theory of everything, and this works for all physics beyond the coherence length, you can't, once you look at that, immediately predict its remarkable consequences, okay? When this was first written down, the physicists who wrote it down weren't even sure how real psi was. And for more than 10 years, it was thought of as a mathematical convenience. After all, if this thing can be changed by a gauge transformation, how can it be real? Things that vary under a gauge transformation are not real objects. And yet, history has shown us that those who've been naive enough to think of the order parameter as a real quantity have had the upper hand. Abrikosov used that thinking to come up with the idea that you'd get a flux lattice. And when he showed his results to Landau, Landau poo-pooed it, and he was so upset and so worried he just threw it in his drawer and left it there for 3 or 4 years before bringing it out again. Yeah? The young Brian Josephson was naive enough too to think of this as macroscopic quantum mechanics, and he used it to deduce the Josephson effect, an effect which even the most liberal followers of superconductivity of the time, such as Phil Anderson, were hesitant to accept initially, okay? And so, whilst it is true that this quantity here is not gauge invariant, okay, it turns out that all gauge invariant quantities that come from thinking about it as real, okay, are physically measurable. And so it's very, very useful to go forward in treating this as a real variable, okay, right? And in the end, it's not so very different to living in our physical world where we think of position as an absolute variable. It's not, of course, but we use it practically. We take the gauge of this seminar room and we work in this Newtonian picture with a definite Cartesian reference frame as a valuable way of going forward. And so we're going to think of this quantity as a real variable, an observable quantity. Okay. Now, great. What else do I have to say? Oh, so beyond the coherence length, this Ginsburg-Landau theory predicts that there are basically beyond the coherence length, only phase fluctuations dominate. Phase dominates in this region here. And down below here, amplitude fluctuations turn on. Okay? So I've lost my very nice picture of the Mexican hat, but we basically have amplitude fluctuations and we have phase fluctuations. Okay? Let's look at what happens and is predicted by this theory here. Okay? If we write out the theory in terms of amplitude and phase, let's look at that. If we write psi equals mod psi e to the I phi, then d psi, this is d psi, here we can pull the phase out and write it as gradient of modulus of psi plus I mod psi times gradient of the phase minus E over H A. And so you can see that this kinetic energy term contains a amplitude, real part, and a phase fluctuation, imaginary part. So that if I now write d psi squared, modulus, this phase term vanishes, and I can separate this out as a phase term and an amplitude term. And so once you've done that, you can separate the Landau-Ginsburg theory into two terms. F psi, F psi, the Landau-Ginsburg part, now looks like this, F psi. We're going to write it as rho s over 2 grad phi minus E star over HA squared. Okay? And then we're going to write everything else plus H bar squared over 2m grad psi squared, grad modulus of psi squared, plus R modulus of psi squared, plus U modulus of psi to the fourth. Okay? And the phase stiffness that comes into this is now minus E star over H bar A. And the phase stiffness, rho s, that is here, is just all the quantities that we had in front. Yes, let me just finish and write phase stiffness. Let me just write this in. Yes.
Unfortunately, you just erased it.
Oh, thank goodness. Yes, because it's the modulus of this complex number squared that comes in here. This is the modulus of grad. There's this, sorry, there should be a, there you are. That's the modulus that comes in there. So the mixed terms vanish because it's the modulus squared. Good, okay? And so what you see here is that this term here is the term which I can write as 1 over psi squared, like that, okay? This term here, these fluctuations have a length scale given by the coherence length, okay? So beyond the coherence length, you lose the amplitude fluctuations, and so you might as well just use this term at long distances, okay? And this term just depends on the phase. And so that's why at very long distances you can basically scratch this term out of your theory, okay? And phase dominates, okay? And if you want to deal with this action legally, you should treat it like you do in classical mechanics. You should take variations of psi and variations of A and set them equal to 0, and that gives you your equations of motion. Okay? Let's just look at that very, very briefly. Let's take variations of A. If we take variations of A, then dF is dF psi plus dF electromagnetic. Okay? Now, if you do this without this term here, okay, you just get the equation of a magnetic field in free space, and you just get the curl of B equals 0. But if you do this, turns out that this gives you nothing more than it's proportional to A, and the term that comes in here has to be equal to 0. So when you vary dF psi, that term, dF with respect to dA, or dF psi, just gives you dA of x times the current at position x, with a minus sign there. And so what you get when you do this is you get J of x, and then some other term here, but you know this has to give you Ampere's law, right? Because the relationship between J and the curl of A is Ampere's law, and so you can almost guess that what you're going to get here is curl of A over mu naught, okay? Now, to actually check that that's the case requires some muscle, okay? This part here is quite easy to do, okay? You can very easily see that dF psi, just taking this term here, just comes from differentiate this with respect to A. And so this is very clearly d cubed x dA, or ddx, dotted into, and now just pull out the terms that you have here, and you get nothing more than minus E star over H rho S grad phi minus E star A over H bar. And so you can recognize this as the current, J superconductor. Okay? This term here, to do that requires a little bit of work differentiating grad A squared. Okay? And I'm not going to do it for you. Okay? If you want me to show you on the blackboard, there's some minor sign issues. You have to take a total derivative, extract a total derivative and set that equal to 0. And when you've done all of that, you get this minus curl of A over mu naught. Right? But coming out of this then, of course, is nothing more than when we now calculate this that now gives us that sorry, my mistake, this is curl of B, not curl of A. Okay? Curl of A is what comes out of that. And so when you finish with all of that, you then have nothing more than Ampere's equation, mu naught, but what comes in here is now your ns E star squared over m, and A minus H bar over E star grad phi. And so you can see that although the phase by itself is not measurable, this gauge invariant combination of phase and vector potential is a measurable variable. Okay? This is nothing more than the current. And from this, we immediately extract the fact, if I take the curl twice, we immediately extract del squared equals minus 1 over lambda L squared B, okay, which confirms that 1 over lambda L squared is mu naught, Ne squared over M. Okay, I want to end by talking about upper critical fields and vortices, okay? And we won't quite finish that today, so we'll finish it all next time. But you may remember that dramatic picture of the suspended... Oh, any questions before we go on? Yeah. Yes.
You only included even powers, and I understand that symmetry argument.
Yes.
Why would I not go beyond the fourth order up to the sixth order?
Well, of course you should, in general. And so this is only an approximation, valid when psi is very, very small. In BCS theory, when you work all of this out, you get a trace of a log of a Green's function, which you can expand in powers of delta, and also time-dependent parts of delta, of the order parameter. So in general, it's a much more complicated thing than this. This is only really universal close to TC. Nevertheless, it can be used as a cartoon for well away from TC. Okay? And so we're really using it in that second context. We're saying, oh, let us believe this occurs all the way down. Of course, were this a relativistic theory or something like that, it might be true. If this were a true particle, it might be exactly true. But in superconductors, it's certainly only an approximation. Yeah. Yes?
So if I have a system that goes through a phase transition that,
Yes.
that leads to the formation of vortices,
Yes.
something like the XY model, and
Yes.
then the temperature,
Yes.
then it makes sense that the free energy goes down when you form these things, but what's confusing to me is how they actually form. Do we have much information about the dynamics of how they're created?
So I think what you're saying is the following, is that I imagine taking this system at some point, the order parameter forms at some high temperature, and now when it forms, there will somehow be vortices there. How do they form? Okay, right? It's a little bit like saying, how does a hurricane form? Hurricane form. You might have some small ambient circulation in the system, some net circulation in some area. As you cool it down, that circulation has to quantize in a superconductor. So it has to split up into little vortices, okay? Basically because the superflow doesn't allow any curl of V. In fact, you can see that if we look at this expression here, if we take this away, the curl of this V is the curl of the gradient of phi, but that's 0, okay? So the only place where the curl can survive is in the core of the vortex. And so it immediately condenses all of that vorticity into localized units, each of which has one quantum of vorticity, and that's what we're going to talk about next, okay? Right? We already saw that vorticity was quantized because when you integrate V around a loop in a neutral superfluid, you get the change of phase times h bar over m, and the change of phase is quantized, right? But if we now do that for a superconductor, we also have to integrate the vector potential around the loop. And when you integrate the vector potential around the loop, you get by you get from vector calculus that that's equal to the integral over the area of the curl of A, which is nothing more than the flux. And so let's go and do that little calculation. This will set us up for next time. We're going to talk about vortices, flux quanta, and type 2 superconductors. And I'm just going to write down the key points here. And superconducting vortices and type 2 superconductors. And in a type 2 superconductor, the penetration length is bigger than the coherence length. Okay? So the first thing we're going to discover is that flux in a superconductor is quantized in units of phi naught equals h over E star, which of course in our world is h over 2e. Okay? In a nuclear condensate, where you could in fact have something with an odd number of electric charges as a boson, still possible, okay? You could have different flux quanta. So that's flux quantization. Okay, and here's the basic picture that goes with it. We have a superflow of current forming a vortex, okay? And we have flux running through here, phi naught equals h over E star. Now, in a neutral vortex, the current is just the gradient of phi, and the gradient of phi is 2 pi divided by 2 pi r, or 2 pi n divided by 2 pi r. So in a neutral superfluid, you get h over m times 2 pi over 2 pi r, or 2 pi n times 2 pi r, which means that the superfluid velocity decays as 1 over r. That's very costly because the energy of that is then 1 over r squared times r dr, which gives you a logarithmically divergent energy. So one vortex in a superfluid costs a logarithmically large amount of energy, okay? Which is why they like to form in pairs, okay, right? Or if they're already there, they don't care, right? But in a superconductor, you can remove the strain of the supercurrent by adding in a magnetic field. And so magnetic fields like to be attracted and pinned inside vortices, okay? And so what happens in this game, let's look at what happens, is that when we look at the rotation, this is the circulation, which is dx dot vs, then we get two terms. One is h bar over m times dx dot grad phi, and the other term is minus e star over m times dx times a, okay? By Stokes, so this thing here is nothing more than 2 pi n, okay? By Stokes' theorem, this thing here is ds dot the curl of A, which is nothing more than the flux, okay, through the loop, okay? And so this whole thing here is nh over m minus E star over m times the flux through the loop, okay? Right. So now, very far away from this vortex, what happens is that the circulation disappears, okay? Because the vector potential comes in from this flux here to exactly cancel the gradient of the phase, right? And so let's look at what that means. That means that this term has to cancel this very far away. So in the limit that the radius of this loop goes to infinity, that means we have to have 0 equals nh over m minus E star phi over m. And that then means that phi has to be equal to nh over E star equals n phi naught. This is not a cosmic law. This doesn't say that all fluxes have to be quantized. It says that inside a superconductor, to minimize the energy of this vortex, we must have the circulation, we must have phi equal to an integer number of flux quanta, okay? And this is sort of where I'm going to end, but you can measure this. What you can do is you can take a cylinder of superconductor and pass a magnetic field through it with an external coil. Here it is, okay? This is the superconductor. Okay, and what happens is that when you apply an external magnetic field, this thing loves to trap an integer amount of flux. The other stuff it just expels outside, okay? And so delta phi, so phi running through here is, the flux running through here is n times h over 2 E star. And the way you can see that experimentally is you can actually measure the amount of flux running through it as a function of the external field. And here is the flux divided by h over 2e. And normally you'd expect it to go just a nice straight line like this, but it doesn't do that. In fact, what happens is that it quantizes. And so it just jumps. It stays 0 here. Then it jumps up, stays there. Then it jumps up again. Versus h here. And so this is the phenomenon of flux quantization. And it can actually be experimentally observed, and it was probably first observed by Fairbanks et al., probably at Duke University. Fairbanks later on took this methodology to Stanford, and he used it as a monopole detector. A monopole has a net flux, of course. So when one monopole goes through here, it means you change the flux through this by 1 unit, and you see a jump in the current running round it, okay? And this jump in the current was only observed once in history, which is quite probable because there are very few monopoles in the world, or it could alternatively be because it was April the 1st. No one really knows. Thank you. Yeah, we're done for now. We have 4 minutes for questions. We covered a lot. Yes?
I have a stupid question. Why did you say that the expected linear behavior?
Oh, simply because if the flux lines were not distorted, the flux through a loop would, in a metal, you would expect it to be linear because the flux lines from the external coil would just go straight through this superconducting, through this loop of conductor, and there would be no reason to be quantized. In a metal, flux is not quantized. Okay, right? But because the superconductor doesn't like to have currents running round here, okay, what it does is that I'm not going to have any currents. I'm going to adjust my A so that it exactly cancels the amount of the amount of twist in the wave function, and that means that's what's going on here. Yeah.
No, that's why I just wanted
Yeah. Good.
to definitely the expected
Yeah.
behavior.
Yeah. Okay. Any other questions? I'm around. Ask me questions. Grab me at lunch. Okay. Thank you for being a good audience. Yes.